Hi all, welcome to the tech session on sensorless control of PMSM motor. To achieve this, we will leverage the strengths of two powerful software tools here today. PSIM for power electronic simulation and Altair Twin Activate for system level modeling and co-simulation. Today in this problem we are developing an sensorless control for PMSM motor to eliminate the use of physical sensors. So here we see the project overview. We will be developing an high fidelity PMSM model using the PSIM software and via a ROM model development using the Activate. Here we will be leveraging the reduced order modeling with AI to replace physical sensors by enabling virtual estimation of rotor position and speed. Coming to the control topology used for the PMSM motor control, we are using the field oriented control. The FOC here allows independent control of motor torque and flux by decoupling torque and flux components of stator current to achieve precise control of AC motors. So here we will be using the Clark and Park transformations to calculate the VD VQ values. Based on that, we will be calculating the switching frequency for switching frequencies, which will ultimately control the current into the PMSM motor. So this is the basic understanding of FOC control. Moving on, I will be like taking you to the schematic of PSIM, like PMSM motor drive circuit here. So this you're seeing here is the interface of PSIM software. We have developed this motor drive schematic circuit for PMSM motor using PSIM. So it has wide variety of components here. As you can see, we have the spark plug transformation blocks, PMSM motor blocks, everything. So using all this, we have developed this motor drive circuit for PMSM motor. So the circuit you're seeing here is the most traditional way, like the method where we use the censored control. Here what you see omega m is nothing but it replicates the sensor here, where we calculate this speed here, and this here specifically gives the rotor position. So if you see the control topology here, we use the omega m and the rotor position sensor to, like, the omega based on the speed that is like seen there. Based on that, we are calculating the VD and VQ values here. Later with taking consideration of the rotor position sensor, etc., we use the Park Clark transformations, and we come up with the switching frequencies for the switches, and the current is controlled for the PMSM motor. So here the main important part here, it is the calculating the speed of the motor here, based on which the rest of the calculations proceed. So for that, we are using a sensor in the motor here, so which will like sense the speed and set the data to the control part here. So accordingly the like process takes place and the control of the PMSM motor is achieved. So this is the traditional way of using it. Here in this session, we will be seeing how we can achieve this without the use of this sensor here. How can we calculate this data without using a sensor in the motor? For that, what the main requirement to develop this ROM model is, we have to generate a training data, which we will use to train the ROM model. So to generate the training data, we are using HyperStudy. HyperStudy is a software where we will be doing DOE, like design of experiments, where we are able to define our own, like define our input variables, define output responses. Based on that, we will be getting our required outputs here. So more specifically, here we are like defining omega m reference as our input variable. In the output responses, we are defining all these output responses here. So coming to the specifications here, so what we see here is the different types of DOEs, like the fractional, factorial, full factorial, etc. So what we achieve here is, so when like we understand how different factors like influence an outcome more effectively here. Instead of testing each and everything randomly, it helps us to focus on only the important combinations here, like as I have talked before, like defining the input variables, defining output responses, etc. So here what we do is, after doing all this, we like choose the suitable DOE, like the fractional, factorial, etc. After that, we define the number of runs here, like 11 number of runs and all. After doing all this, once we evaluate, it runs for 11 consecutive runs as specified earlier. So we get this 11 runs, and based on that, this data is like these maps are generated, the 3D scatter maps, the plot media, and many other stuffs here. So what we are mainly focused here is, once we are done with evaluating and post processing, we get all these graphs here, like omega m on different values, like 140, 180, 220, like on different. So you see all these different values here, right? It is varying on various, on a range now, 110 to 210 on different fidelities. Like we are able to vary this. So this is what we want to train a data, like to train a model, ROM AI model. So once we do this, we end up with a text file here. If I have to show you the text file, uh, so a text file like this, we end up with a text file like this, which has like PSIM model run test results here now, generated using hyperstudy. So this is what we have achieved using the hyperstudy now, like the text document where we have 11 runs, like 11 runs here with the results there on a text file. So that text file can't be directly used to be like fed into the ROM AI model. We cannot feed it directly. So we have to convert it into CSV format. For that, we are using Compose is like used for mathematical, like scripting, mathematical model development, or process automations, etc. So this script here is used to generate a CSV file. Now if we have to edit these three lines here, 6, 7, 8, 9. Here we are specifying the path of the file, the name of the model, the name of the PSIM file, the result file which we have achieved using hyperstudy just now. So that same file name we are specifying here. So based on that, now this will generate a CSV files now. So the CSV files it will generate will be like, once we run this script, it will generate CSV files for the runs we have done before. So we will be achieving all these CSV files for 11 consecutive runs. There are 11, like 11 CSV files for all the runs that we have done here. Like 1 to 11, there are 11 different CSV files for that. But we will not be feeding all this separately. We have to merge all this into one and then feed into ROM model. For that, we will be using another script here. Sorry, this one. So what this script will do is, it will merge all the data into one file called merge.csv. Once we run this script, we will end up with this final CSV file merge, which we will be using to develop the ROM AI model here next. So now moving on to tin activate. Now to develop that ROM AI model, we have to load the data now. To load that data, we are going here, this merge, and this is it. We have got all the parameters like input, output. So we have to specify inputs and outputs now. So ID, IQ will be the inputs, VD, VQ will be the inputs, omega m int omega m, this will be the outputs and also the states, and we will be putting this as state derivative. So we have to name this model. The model will be named as sensor. So this will be the name of the model here. So coming down to this block here, what you see here will be specifying the model type here, like linear, non-linear, auto exploration, etc. So this will be specifying for the ROM AI model what deep learning method it is going to take. So here we'll be putting 10 repetitions, 30 epochs. That's it. We will give the run. So what happens here, it is, it will generate 10 different models, and in that 10 different models we will be selecting one of the models here, the most accurate one. So that's how we'll be doing it. Now coming to this here, um, okay, so what you see here is the final sensorless control schematic in Connectivity here. We are using this as a co-simulation like for PSIM. So here is the ROM AI sensor, this is the PSIM file. So now I will be showing you the PSIM file for co-simulation that we'll be using here. So what the earlier the schematic that I had shown, that there we were using the data from the the omega m, the speed data we were taking from the motor here. But in this we are not doing so. We will be taking this omega m from the ROM AI. Now the omega m, also the rotor position, will also be taken from ROM AI. So to show that, we can see here, what we see here as this is the link node that will be linking it from activate to PSIM here. So what it does is, it takes data from here omega m room. From there it gives into omega m here label, so that will take it and proceed with the calculations here. So based on the data generated from omega m room, this is calculating, the further calculations are conducted. Similarly for the rotor position, earlier we took data from the directly from the motor and we calculated. Now it is taking data from the ROM model that was created. From there it is doing the calculations. So the rest of the nodes you see here, like as these are all the link nodes that are used to connect it with the ROM model here. Say IDIQ, VDVQ, Omega MPSM, CTR MPSM, etc. So you see all that here: IDIQ, VDVQ, Omega M, CTR. This is for the linking purpose here. These nodes are used. So we can see here our ROM AI model development is done. If we come to this, okay, it is done here. So the name we had given was sensor. So I have done many runs, because of that we are having so many things. If we have to focus on only these ones here, so it has done developed 10 models here. So how do we choose the most accurate one? What we do is, we go through this test loss index and choose the one with the lowest text loss index. So in this, if we have to choose, it will be 1.4. Sensor 1, this will be the one. Like if you see my previous runs, we can see we have run this model named like ROM model that we have developed. In that, in 10 consecutive runs, we have model 1 as the most accurate one. It has least low test loss index. So similarly, so this model we will be using, I mean if we have to run CR model, we will be using this as the model for ROM AI here. So that model will be fed in here, and the further calculations, like it will carry on with the further process. Now if you see the simulations result for this one, we will be comparing the ROM what do you say, the ROM calculations, I mean the ROM model prediction, and the censored one prediction. So if we see here, uh, Okay. I'll be taking omega m ROM and the omega m 5D screens. Okay, so if we see the omega m ROM is like clearly following the path of omega m. So this is what we have achieved using the sensorless control here. So this says our ROM model is 100% accurate. If we see the green line, you will be able to differentiate here. So our model is almost accurate. The model we have generated, it is almost accurate. So we can see the other graphs also here, like the CTR, like the rotor position here, that is also following. Other than that, if we have to compare these, so we are getting accurate results here. If I have to show this, so this is what we have achieved here. We are getting our model that we have developed is nearly 100% accurate, which is following the required path here. Now, if we compare it now, omega with the omega reference, it is exactly showing the same behavior here. So we can conclude that the ROM model developed is nearly as accurate as the censored one. So with that, I'll be concluding this session. Thank you.